Good afternoon. MATH113 section 7. Today is day number 25 into the semester, week number 13. Week number 13. By the end of next week, we're going to finish the semester. And by the end of next week, you have to submit the project work, the proposal, the report, and the PowerPoint, covering 20% of the extra item of the project. And then remember, the final exam is on December 18th, which is Friday, 9:30 to 12:30, and the location is called E2, G007. Okay, you need to check it out. Where is E2? Right, so today, let's get started by giving you a problem to think of. It's a problem based on the concept of optimizations that we have been learning. And this time is a problem which requires you to use implicit differentiation. So pick up a piece of paper and a pen and try to work this out, okay? It's at least an important practice before we get to the topic of the day.
Hi, welcome back to In lecture, you've been doing related rates problems. I've got another example for you here. So this one's a really tricky. I'm going to give you some time to work on it, but I really think you should really try and work through this for yourself. It'll be well worth your effort. So we've got here, we've got a 20-foot long ladder, and it's leaning against a 12-foot wall. But it's leaning over the wall, so 5 feet of the ladder project over the top of the wall. And then the bottom of the ladder is being pulled away from the wall at 5 feet per second. So the question is, while this is going on, how quickly is the top of the ladder going down? How quickly is it approaching the ground? So why don't you take a few minutes, maybe more than a few for this one.
Can you draw the picture?
Take a few minutes, work this one out, come back and we'll see how.
Draw the picture, extract the information, and then try to think of it. How can you put into perspective the information given? How can you work out the solutions based on the concepts of derivative? You have a wall, okay, which is 12 feet long, or tall, I'm going to say, and you have a ladder, which is 20 feet long, longer, but it's higher than the wall. And it's going to put something like this, with 5 feet projected out of the wall. And then the ladder is going to slide down with a rate of 5 feet per second. Welcome back. So how quickly is the top of the ladder approaching the ground? Okay, you're calculating this with the concept of derivative. All right. So, can you try to do it in 5 minutes? Very simple questions. Now, please put some thought into questions of this type, which you can produce as your project type of questions. All right. Who's thinking about the project questions? Go team. What kind of relationships can we use to represent those figures? The distance, the length, right? It will be very interesting to come back here and then serve you with a practice problem. Make sure you think about this. And you need to practice volunteering questions at this time in your group discussion so that you know what what particular problem you want to work with in your project. And I highly recommend optimizations because it's very good for you to put some perspective into what you've learned so far. We're giving you 10 minutes time to work on this question. So we're going to solve you the solutions, but it's 2:45. Hopefully you got something out of it already. Well, it's in the area of optimizations, so you need to think about the relationship where you can connect those data together in the form of some kind of expressions, and then you need to find a suitable entity in which you can perform the differentiations and set a derivative of that differentiations to zero in order to test the maximum or the minimum values of it. In this particular case, the question is how quickly is the top of the ladder approaching the ground? Okay? Top of the ladder approaching the ground means what? Sliding relationship. When the ladder approaches the ground, some distance or some length is going to be zero. So the question is how quickly you find the rate of something, right? So let's be more patient. Look up the informations. how much of the formulations you can produce without looking into the solutions first. Of course, you can discuss with your table members. It's a very healthy thing to do, to put together ideas, thinking, and techniques. Okay, let's go back to the tutor.
All right, so hopefully you've had some luck working out this problem on your own. Now let's work it out together. So, okay, so this is a sort of classic, really tricky related rates problem in that there's a lot of geometric work that you have to do at the beginning in order to get this right. And then once you get the geometry down, the calculus is basically totally straightforward. You need a couple of derivatives and chain rule one way. So let's start off by trying and drawing a careful picture, and then we'll have to figure out what the quantities that we're interested in are and the relationships. So we have here's the ground, and we have a 12-foot wall. And we have a 20-foot ladder leaning against the wall and extending over it. So, my ladder. So here's my ladder. Here's my wall. And this, the bottom of the ladder here, is what's getting pulled away from the wall at 5 units per second, 5 feet per second. So 5 feet per second is how fast that's going. And we're interested, so while you do that, the ladder is changing position. So the question is, how fast is the top of the ladder descending? So, it might also be moving in some other directions, but we're just interested in how quickly it's going straight down. So, okay, so first let's talk about the things that don't change. So the height of this wall is not changing. The wall is staying put the whole time. And the length of the ladder is not changing. That's staying put as well. But those are the fixed quantities in this problem. Basically everything else is changing. So for example, this distance between the base of the wall and the base of the ladder, that's changing because the ladder is being pulled away from the wall. So we can give that a name. Let's call that's a horizontal distance, so we can call it x, say. And the height of the top of the ladder is changing. So let's draw that in. That's what we're interested in. It's the height, so we can call it y. And let's see what else. Well, okay, so the whole ladder isn't changing in length, but as this gets pulled, this top point is sort of sliding down toward the wall. The amount of ladder that extends over the wall is changing. So I guess we could choose. We could give this a variable name, or we could give this part a variable name. I think I'm going to give the little one a variable name. I'll call it d, or distance, I guess. And okay, so this is d because the whole ladder has length 20. We have that this segment has length 20 minus d. Okay, so I think that those quantities describe all the possible lengths of interest in this picture. So now, okay, so that's just the setup, right? So that's the first thing that has to happen. Now after we've set up, we need to figure out what the relationships between these different variables are. So, well, let's see. What have we got? Well, one thing we've got is that we've got a right triangle here. So the wall and the ground and the ladder, those three segments form a right triangle. So, okay, so we can apply the Pythagorean theorem here. So that's one relationship we have, and that's going to give us a relationship between x and, well, okay, 20 minus d. So that'll give us a relationship between x and d. So this Pythagorean theorem, okay, so what does the Pythagorean theorem say? So by the Pythagorean theorem, we have x squared plus, well, that's a 1. 12 squared is equal to the quantity 20 minus d squared. So that's one identity that we have that relates these three quantities. So that's good, because we know how fast x is changing. And so with this identity, that means we can use related rates to figure out how fast d is changing as well. So that's good. That'll be a step in the right direction. But what we actually need to know is how fast y is changing. Right, because that's what the question is asking for, how quickly is the top of the ladder approaching the ground? So what's the rate of change in y with respect to time? So I need another identity here in order to figure out what the relationship with y is and these other variables. And there are a couple of different ways to go about this. I think the one that I'm going to do, so there is another right triangle here. So you could, if you wanted to name this segment as well, then you could do another right triangle, but then you'd need a third relationship relating this segment to d or something. So I'm not going to go that route, but I'm going to go do something related to that, which is that this bigger right triangle, right, which has the height of the top of the ladder from the ground and the whole length of the ladder is 2 of its sides and a piece of the ground. So that bigger right triangle is similar to this smaller right triangle. Right? I mean, they have, they're right triangles and they have the same base angle there. So they're similar triangles. So by similar triangles, now I have to remember all my geometry, right? So the ratio of corresponding sides are equal. So in this case, the ratio of the hypotenuses is equal to the ratio of these legs. And that'll relate, so the hypotenuses involve d, and the vertical legs, well, one of them is just constant, and one of them involves y. So that'll set up a relationship between d and y. And so then I'll have x linked to d, and I'll have d linked to y, and so then we can use related rates to figure out what the relationship between y and x is and figure out the thing we're after, which is the rate of change in y. So I haven't actually written anything down yet. So what is the similar triangle? So here let's look at the hypotenuses. So the big hypotenuse has length 20, and the small hypotenuse has length 20 minus d. Good, so that's the ratio of the hypotenuses, and so that has to be equal to the ratio of the corresponding legs. And so the big leg is y, and the small leg is 12. Okay. All right, so there's Pythagorean theorem, there's similar triangles. So we now have the relationships that we're after, relating x and y and d all to each other. Great. So now we can do the calculus part of this problem, right? So now we know, I guess we need a few more things. Take it back. So now we need the condition. We're after this at a particular moment in time. And at our particular moment in time, so I haven't used this one given yet, that 5 feet of the wall, 5 feet of the ladder projects over the wall. So okay, so at our moment, so at the key moment, we have that d is equal to 5. Okay, so that means 20 minus d is equal to 15. What else does that mean? So that means that at that moment, x in this right triangle is the third leg in a right triangle with hypotenuse 15 and one leg 12. So that's one of your 3, 4, 5 triangles, but blown up a little bit. So we have at that moment that x is equal to 9. And okay, so at that moment to figure out y, we can use this other relationship that we have. So 20 over 15 is equal to y over 12. So y is equal to, well, 20 over 15 times 12. So that's 4 over 3. So that's 16. So at our key moment in time, these are the values that we're going to end up plugging in. And also, dx dt is equal to 5, right? X is being increased, yeah, x is, right, this, so as the foot gets pulled away, x is getting bigger, so x is being increased at 5 units%. All right, so these are all the things we're going to plug in. All right, good. So now we are after dy dt at this moment. And we don't have a, so we know dx dt, we don't have a direct relationship between y and x. We do have a direct relationship between y and d. So if we got dd dt, then we can get dy dt. And because of this relationship, we can get dd dt. All right, so let's start off by doing that. So, okay, so this is an identity. It holds always, so we can differentiate it. And we're going to differentiate it with respect to t. X and d are functions of t. So, okay, so differentiating this identity, I get 2x times dx dt plus, well, okay, derivative of 144 with respect to t is 0, is equal to, I guess I could expand this out, but it's easier just to use the chain rule right away. So this is equal to 2 times 20 minus d times the derivative of 20 minus d with respect to t, which is minus d d dt. All right, I beg the gods of math notation to forgive me for d d dt, but okay. So all right, so now, so this is always true, and what we want is the value of d d dt at our particular moment in time. So at our particular moment in time, we have, well, let's see, okay, so we have x, we have dx dt, and we have d. So we can just plug all those things in. So at our moment, let me see how I'm going to do this. I'll do it over here. At our moment, so 2x is 18 times dx dt is 5 equals 2 times 20 minus d is 15 times minus dt dt. And dd dt is what we're after, so okay, so we just divide through, okay, so divide 2 into this is 9, 45 divided by 15 is 3, so d dt is equal to minus 3 at the moment that we're interested in. All right, great. Great, so now we have dd dt, and so now we can go back to the second relationship we have, the one that relates d and y, and we can do the same thing here. We can take a derivative, use the chain rule, use and get a relationship between dy dt and d and dd dt. And then we'll be able to plug in all these values we have for our particular moment. So okay, so I think I'm just gonna differentiate this straight. There are some simplifications I can do first, but it'll work fine if we just do it straight. So okay, so I need to compute the derivatives. This is an identity. I can take its derivative. So I differentiate the left-hand side with respect to t. So I get 20 over, so this is a minus first power, so minus 20 over 20 minus d quantity squared times, I need the derivative of the bottom is minus dd dt. And on the right-hand side, I get dy dt over 12. So I have this relationship between d and y. I take its derivative, now I have a relationship that involves dy dt, which is the thing that I'm after. So, so now I'm back to just plugging in the stage. So at our moment in time, I know what d is, and I just figured out what dd dt is, so I can just plug those values in to figure out what dy dt is. Okay, so let's do that. So at this moment in time, we have, so let me just multiply through by the 12, and that let's solve. So we have dy dt is equal to 12 times, well, so it's minus 20 over 15 squared times minus 3 times 3. So this is arithmetic. My favorite thing in the world. So we got 2 3's here. We got end up with a 5 in the denominator, and then we've got 4 times minus 4. So that's minus 16 over 5. So, all right. So that's the answer. Let's remember what we've done. So minus 16 over 5. That's a negative number. Why is it a negative number? Well, as we pull the bottom of this ladder here away from the wall, the top of the ladder is going to fall downwards. It's going to get closer to the ground. And y is the vertical distance between the ground and the top of the ladder. So that's shrinking. Y is shrinking. We should have a negative derivative. Okay. Negative derivative, minus 16 over 5 feet per second. So it would take, if this instantaneous rate held up, which it won't in this situation. If it held up, it would take 5 seconds to get down, so it's not falling very quickly. Okay, that seems about right. Anything else? Oh, I guess we computed that dd dt was also negative. Same thing here. When you pull this way, this length is going to shrink. So d is getting smaller, so it has a negative derivative. Okay, so at this moment in time, the top of the ladder is falling, the thing we're interested in, at exactly 16 over 5 feet per second. And what else?
How many tables are getting in this particular direction? It's a very simple but very intricate process to nail down those relationships. Now let's get back to the method. I would like you to learn, and actually this is a method very interesting. It's called linear approximations. Welcome back. You're just in time to begin the lessons. Okay, so first let me give you 15 minutes, and then I'll give you the second half, all right?
Method, which is one of the greatest applications of calculus.
Newton's method.
And I'm going to describe it here for you, and we'll illustrate it on an example, which is solving the equation x squared equals 5. Okay, we're going to find the square root of 5. Now, you can actually solve any equation this way. Any equation that you understand, you can solve this way, essentially. So even though I'm doing it for the square root of 5, which is something that you can figure out on your calculator, in fact, this is really at the heart of many of the ways in which calculators work. So the first thing is to make this problem a little bit more abstract. We're going to set f of x equal to x squared minus 5. Okay? And then we're going to solve f of x equals 0. So this is the sort of standard form for solving such a. So you take some either complicated or simple function of x. Linear functions are boring. Quadratic functions are already interesting. And cubic functions, as I've said a few times, you don't even have formulas for solving, so this would be the only method you have solve numerically. So here's how it works. So the idea, I'll plot this function. Here's the function. It's a parabola. Y is equal to x squared minus 5. It dips below 0. Sorry, it should be centered. Okay? And now the idea here is to start with a guess. And square root of 5 is pretty close to the square root of 4, which is 2. So my first guess is going to be 2 here. So start with initial guess. All right? So that's our first guess. And now, what we're going to do is we're going to pretend that the function is linear. That's all we're going to do. And then, if the function were linear, we're going to try to find where the 0 is. So if the function is linear, what we'll use is we'll plot the point where 2 is on the, that is the point x, 2 f of 2. And then we're going to draw the tangent line here. And this is going to be our new guess. X equals x, which I'll call x1. All right? So the idea here is that this point may be somewhat far from where it crosses, but this point will be a little closer. And now we're going to do this over and over again and see how fast it gets to the place we're aiming for. All right? So we have to work out what the formulas are, and that's the strategy. All right. So now, the first step here is we have our guess, we have our tangent line, which has the formula y minus y0 is equal to n x minus x0. All right? So that's the general form for a tangent line. And now I have to tell you what x1 is in terms of this tangent line. x1 is the x-intercept. The tangent line, if you look over here at the diagram, the tangent line is the orange line. Where that crosses the axis, that's where I want to put x1. All right, so that's the x-intercept. Now, how do you find the x-intercept? You find it by setting y equal to 0. That horizontal line is y equals 0. So I set y equals 0, and I get 0 minus y0 is equal to n times x1 minus x0. So I changed two things in this equation. I plugged in 0 here for y, and I said that the place where that happens is going to be where x is x1. All right, so now let's solve. And what we get here is minus y divided by, y0 divided by m is equal to x1 minus x0. And now I can get a formula for x1. Right? So x1 is equal to x0 minus y0 divided by m. All right, now, I now need to tell you what this formula means in terms of the function f. So first of all, x0 is x0, whatever x0 is, and y0, I claim, is f of x0. And m is the slope at that same place. So it's f prime of x0. And this is the whole story. This is the formula which will enable us to calculate basically any root. Okay, I'm going to repeat this formula. So I'm going to tell you again what Newton's method is and put a little more colorful box around it. So Newton's method involves the following formula. In order to get the n plus first point, it's a better and better guess, I'm going to take the nth one, and then I'm going to plug in this formula. So f of xn divided by f prime of xn. So this is the basic formula, and this is, if you like, this is the idea of just repeating what I had before. And we've gone from geometry, from pictures, to an honest-to-goodness formula which is completely implementable and very easy to implement in any case. All right, so let's see how it works in the case that we've got, which is x0 is equal to 2, f of x is equal to x squared minus 5. So let's see how to implement this formula. So first of all, I have to calculate for you f prime of x. That's 2x. And so x1 is equal to x0 minus, so f of x would be x0 squared minus 5. That's what's in the numerator. And then the denominator, I have the derivative. So that's 2x0. Right? And so all told, well, let's work it out in 2 steps here. This is minus a half x0 for the first term, and then plus 5 halves over x0 for the second term. And these two terms combine. So we have here a half x0 plus 5 halves with the x0 in the denominator. All right, so here's the formula for x1 in this case. All right, so now I'd like to show you how well this works. So first of all, we have x1 is a half times 2, plug in x0, plus 5 fourths, right, which is 9 fourths. Okay, and x2, I have a half times 9 fourths plus 5 halves times 4 ninths. Right, that's the next one. And if you work this out, it's 161 over 72. Right? And then x3 is kind of long, but I will just write down what it is. So you can see it's a half of 161 over 72 plus 5 halves, and then I do the reciprocal of that, so 72 over 161. Right? So let's see how good these are. All right? I carefully calculated how far off they are somewhere on my notes. So I'll just take a look, see what I said. Oh yeah, I did do it. Okay, so what's the square root of 5 minus, so here's n, here's the square root of 5 minus xn, if you like, or the other way around. The size of this. You'll have to decide on your homework whether it comes out positive or negative, to the right or to the left of the answer, but let's do this. So when n is equal to 0, the guess was 2, and we're off by about 2 times 10 to the minus 1. And if n is 1, so that's this 9 fourths, that's off by about 10 to the minus 2. And then n is equal to 2, that's this number here, right? And that's off by about 4 times 10 to the minus 5th. That's already as good an approximation to the square root of 5 as you'll ever need in your life. Okay? If you do 3, this number here, it turns out to be accurate to 10 to the minus 10th or so. This goes right off to the edge of my calculator, this one here. So already with the third iterant, you're way past the accuracy that you need for most things. Yeah, question? How come the x naught disappears? Hang on, folks. We have a question. Let's just answer it. So here we have an x0, and here we have minus a half. There's an x0 squared and an x which cancel. Shh. And here we have a minus and a minus 5 halves x0. So I combined the 1 minus a half, I got plus a half. That's all. Okay? All right. Thanks. We'll have to ask other questions after class.
You got the basic ideas of Newton's method now. Let's try a practice here. Okay, immediately we get into the practice. So the practice is here. Let's see one very important method. All right.
Welcome back to recitation. Today what I want to do is something maybe a little bit more theoretical, but the goal is to show that something that you're going to be repeatedly doing when you use quadratic approximations is in fact true. So I'm going to explain the situation, give a quick example, and then show you what we're setting out to do. So the situation is as follows. We're going to, anytime you see a q of f, that's going to represent the quadratic approximation to f at x equals 0. So what I've done is say q of f I'm going to define to be the thing on the right, which is exactly the formula you were given in class for the quadratic approximation of a function f at x equals 0. So f is approximately the thing on the right near 0. Our goal is to show that if I want to take the quadratic approximation of a product of two functions, that I can do it in a different way. I can do it in the way written on the right-hand side, which actually looks more complicated in this notation, but is in fact easier in reality. So let me explain what's happening, and then I'll give you an example. If I wanted to take the quadratic approximation of a product of two functions, what I want to show is that instead, I could take the quadratic approximation of each individual function, multiply those together, and then take the quadratic approximation of what I get as a result. So let me give you an easy example. For instance, let's let f of x equal e to the x, and let's let g of x equal sine x. Okay? Then what is q of f? Q of f is the quadratic approximation to e to the x at x equals 0, and that's going to be 1 plus x squared over 2. You already knew this. And g, the quadratic approximation of sine x, is just x. So, if I wanted to find the quadratic approximation to e to the x sine x, what I could do, what this is claiming I can do, is instead I can take the quadratic approximation of this function times this function. So instead I can take the quadratic approximation of f, what's the e to the x? 1 plus x squared over 2 times x. That's not a 4, sorry, that's a parentheses. 1 plus x squared over 2 times x. And what is that? The quadratic approximation to that is the quadratic approximation to x plus x squared plus x cubed over 2. And at x equals 0, if I have a polynomial, the quadratic approximation to a polynomial at x equals 0 is just all the terms up to the quadratic term. So I drop off higher order terms. So I just get x plus x squared. So that's the idea. The idea is I have a product of two functions. I know their individual quadratic approximations. And so what I want to do is I want to find the quadratic approximation of this product by exploiting the fact that I already know their individual ones, and exploiting the fact that quadratic approximation of polynomials at x equals 0 is very easy. So that's the example, that's the idea. So now let's see if we can do it. Okay, so we have a cheat sheet up here that I'm going to refer back to. I didn't want to use it again. I didn't want to have to derive this for you, but we have the product rule. Fg prime is equal to what's on the right, and Fg double prime is equal to what's on the right. So my goal here is to show, remember, that the quadratic approximation, let me point over here again, the goal is to show the quadratic approximation of Fg is equal to the quadratic approximation of f and the quadratic times the quadratic approximation of g. So let's do the right-hand side first, because that's a little nicer. And then we'll show the right-hand side, and then we'll show the left-hand side, and we'll show they're equal. So let me start here with the right-hand side. Okay, so let's look at what's the quadratic approximation of f and what's the quadratic approximation of g, and then we'll take their final quadratic approximation. So q of f, we have exactly what we need there. F of 0 plus f prime of 0 times x plus f double prime of 0 over 2 x squared. Q of g is equal to g of 0 plus g prime of 0 times x plus g double prime at 0 over 2 x squared. So now what I'm going to do is multiply those two together. And I'm actually going to swing this way a tiny bit, if that's okay, to write q of f times q of g, because it's going to be a little long. And I'm going to group them carefully so that I have all the higher order terms at the end. Okay? So I'm going to get f of 0, g of 0, if I'm multiplying these two together. And then I'm going to get two terms involving an x. I'm going to get an f prime times g and a g prime times f. Actually, if you'll allow me, we'll know that anywhere we see an f or a g or an f prime or a g prime or an f double prime or a g double prime, they're all evaluated at 0. So I'm going to drop the zeros from here on out. Anywhere you see those, I'm evaluating them at 0. Otherwise, this will be way too long. So let me write this just as fg. I could even write just the single one evaluated at 0. It's the product evaluated at 0. And then I have f prime g. So I'll just evaluate at 0 at the end of the product. Plus fg prime evaluated at 0. This whole thing is times x. I get an x here, I get an x here. Now I need to figure out what terms give me an x squared. Okay? So the terms that give me an x squared are f of 0 times g double prime over 2. That gives me an x squared. F double prime times g gives me an x squared. And f prime g prime gives me an x squared. So let's write out those terms. I get f g double prime at 0 over 2 from those two, plus g f double prime at 0 over 2 from those two, plus f prime g prime 0 all times x squared. So there's an x times an x there, gives you an x squared there, x squared there. Now, I could keep going, and I will mention the higher order terms, but I'm not going to write them all the way out because of what we're about to do. Let me show you where they come from. You get an x cubed term from here, and an x cubed term from here. Maybe I'll write the x cubes, but I won't write the x to the fourth. So the x cubed terms are f prime g double prime 0 over 2 plus g prime f double prime 0 over 2. And those are my x cubed terms. And then I get some x to the fourth terms. And where do the x to the fourth terms come from? They come from this product, right? But I want to point out something. What I'm going to do, I'm going to work some magic on the board. This is the quadratic approximation of f times the quadratic approximation of g. Let me come over here and remind you that I want the quadratic approximation of that product. So what I'm going to do is go back and look at what I need from there to be the quadratic approximation of that product. So if we come back over here, if I apply the quadratic approximation to this thing, which means then I'm applying it to this whole giant thing, what do I actually get? This is actually a polynomial. I have something, I have a linear term, I have an x, I have an x squared, I have an x cubed, I have an x to the fourth. So if I apply that quadratic approximation, let's see what stays. This term stays. This term stays. This term stays. I'm going to erase what disappears because I don't want us to get confused by that. So these two terms disappear. Why? Because again, this is a polynomial. I have linear, or I have constant, I'm sorry, I think I called this maybe linear earlier. Constant linear quadratic term. And what I need is just those if I'm looking for a quadratic approximation. So constant linear quadratic term, I immediately drop the cubic and the quartic term when I'm looking at a quadratic approximation of a polynomial at 0. So if I want the right-hand side, I just need what's underlined in blue. So now I'm going to put a big box around that because that's going to be important. Whatever else happens, we don't want to lose that. So now we've done the right-hand side. And now let's write out what is the left-hand side. And that's just going to be plugging it straight into the formula and using our cheat sheet. So Q of Fg, let me write out the definition and then we'll use the cheat sheet. It's Fg at 0. Again, this is F at 0, G at 0. That's what this notation means. Plus Fg quantity prime at 0 times x plus quantity Fg double prime at 0 over 2 times x squared. And now what we're hoping, remember, is that what's in the box is what shows up over here. Because this is the long way to do the problem. This would be if I took e to the x sine x and I took all the derivatives. And this, in fact, even though it looks more confusing in evaluating such a quadratic approximation, this way would be the easier way. We just want to show we don't lose anything by doing what would be the easier way. So, I get Fg at 0, and that's good. We can see we already have one of those, so that's nice. What do I get here? I get F prime G at 0 plus G prime F at 0 times x. That comes, let me remind you, I'll walk over here, comes from the cheat sheet, the first thing. Fg prime is F prime G plus G prime F. We know that one pretty well, but just to remind you. So that's where this term comes from. This looks promising because if we come back to our quadratic of F times quadratic of G, it looks exactly like the second term here. So now we're hoping that the x squared term looks like this. The only thing that might make you nervous is this doesn't have an over 2, but if you were paying attention to the cheat sheet, you'll probably see where that's coming, and I'll point it out in one moment. So Fg double prime, using the cheat sheet, is F double prime G plus G double prime F plus 2 G prime F prime. I should have put zeros in there. Just to be consistent, let me put these zeros in there. Two F prime G prime at 0. And then I have to divide the whole thing by 2 because there's a divided by 2 there, and then times x squared. So let me move out of the way for a moment. So this numerator came from the cheat sheet for the second derivative. And if you need, we can go back. Let me just remind you, here it is. You can work it out for yourself. You can just take the derivative of the first derivative. But that's where this comes from. So let me go back, and we're almost done with the problem. So what do we see? Well, we see that we get Fg at 0. We get the second term we want, F prime G at 0 plus G prime F at 0 times x. And then the third term is in fact exactly what we want because we get F double prime G at 0 over 2 plus G double prime F at 0 over 2 plus the 2's divide out and I get F prime G prime at 0 times x squared. And if we look at this last term, and we look at the x squared term in the box, we see in fact they are exactly the same. So let me summarize because this was kind of a long video, so I'm going to go back to the beginning, give you the example, and tell you what we were really trying to do here. So let's come back over here and let me remind you, the goal was to show that if I wanted to take a quadratic approximation of a product of two functions, if I already knew their individual quadratic approximations, you were told that you could take those two quadratic approximations, multiply them, and drop off the higher order terms. The higher order than 2. So we had an example. We knew these two quadratic approximations, and you've been told that quadratic approximation of their product is just the quadratic approximation of the product of their quadratic approximations. And so our goal today was to show that you don't drop any of the terms that you get if you do it by this method or by this method. And we've done that. So I think we'll stop there.
It's nice and neat for you to do this particular quadratic approximations expression. Good. Now, Here we go, using Newton's method.
Welcome back to recitation. Welcome back to recitation. In this video, I want us to practice what we're going to do is use what we know about first and second derivatives and what we know about functions from way back in algebra and pre-calculus to sketch a curve. So I want you to sketch the curve.
There we go.
Welcome back to recitation. In this video, I want us to practice using Newton's method to find a solution to an equation. So what we're going to do in particular is we're going to use Newton's method to approximate a solution to the following equation: 2 cosine x equals 3x. And I'm going to tell you where to start. We're going to have our initial value x naught be 5 or 6, and I want you to find x2. So why don't you pause the video, take a little time to work on that, and then I'll come back and I will show you how I did it.
Let me give you some hints first. That's the formula you need, and that's the question you have. Now, first of all, copy the question, and then try to apply the formula. You have 10 minutes time to practice this. Copy the questions, and then put you back to the notes, right? Very simple question. And remember, we start from x0, negative pi over 6, and our purpose is to find x2, okay? 0, 1, 2. Many of you have already spotted on that particular comment. It's a very good example of yes. When you find one, you can always find a second good example, and a third good example, and finish reading with it. You know what you need to do. All right, let me give you the notes. Right here. Try. Now remember there are two separate expressions there, okay? x1 you get x0 minus this, and then xk equals 1 you get xk minus over there, 2, right? Want to make sure you have lessons on this method, linear approximations, and then quadratic approximations. I'm going to take attendance during this period. Ricky, thank you. Johnson, thank you. Stella, thank you. Viviana, not here today. Jordan, thank you. Star, thank you. Chaos, thank you. Lavia, thank you. Louise, thank you. David, not here. Okay. Gertrude, thank you. Viola, thank you. Candy, thank you. Amy, thank you. Alice, thank you. Bella, thank you. Sydney, thank you. Vivian, thank you. Patrick, thank you. Jeanette, thank you. Ivy, thank you. Celia, thank you. Michelle, thank you. Lizzie, thank you. Dart, thank you. Kelvin, thank you. Jeremy, thank you. Andy, thank you. Okay.
Okay, welcome back. Again, what we're going to do is use Newton's method to approximate a solution to this equation. And so what I want to point out first is I want to point out why pi over 6 is a reasonable first value to choose. And I want to point out that this, in fact, has only one solution. So what I'm going to do to give us a reason for that is I'm going to draw a rough sketch of two curves and show where they intersect. And so I want us to notice that if I were to look at the two curves, y equals cosine x and y equals 3/2 x, and I draw them on the same xy plane, that where they intersect will be where I have solutions to this equation. And that's because I just divide both sides by 2. Whatever solves this equation solves the equation cosine x equals 3/2 x. So let me give you a rough sketch of those two curves and we'll see what the intersections look like. So I'm going to do that right down here. Okay. So let me first draw, make this y equals 1, make this y equals -1. And I'm going to draw cosine x first, y equals cosine x first, because I'm most likely to have a hard time with that, and I'll do my x scale once I'm done. And so cosine x, y equals cosine x looks something like this. Maybe not the most perfect, but again, it's kind of a rough sketch. That's pretty good. Something like this. So this is y equals cosine x. And now I want to graph y equals 3x over 2. And that goes through the point 0, 0. It also goes through the point 1, comma 3/2. Well, this is pi over 2, right here. So 1 is about here, we'll say. Because pi over 2 is a little bigger than 1.5. So 1 is about here, 1.5 is about here, or 3/2 if you need to remind yourself. So the line y equals 3/2 x looks something like this. So it's fairly straightforward to see that these two curves intersect at one spot, whatever this spot is. Okay? And notice to the left they don't intersect. So we are just looking for a single solution. And then the other thing I want to point out is why is pi over 6 potentially a good guess to start with? Well, the value, this is the x value 1, and this is the x value 0. We know for a fact that we have to have this x value lying between 0 and 1 because of where my point is at the time that x equals 1, I'm all the way up at y equals 3/2 up here. So at least we know we're between 0 and 1, and then from there you could even try some other values like pi over 3 and pi over 4 and put those in and see how they compare. But at least, we'll just say at least we know x is between 0 and 1, and pi over 6 is certainly in that region. So that's a good first starting point. Now I'm going to come over here and start to do some work. If we want to solve the equation 2 cosine x equals 3x, what we're really doing is we're looking for zeros of this function. So if we find the zeros of this function, which we know there's only one of them, if we find the 0 of this function, then we actually have solved 2 cosine x equals 3x. So hopefully that makes sense to you that we're actually going to apply Newton's method to this function. And so when we apply Newton's method, we need the function, we also need the derivative. So let me remind you, the derivative of this is going to be -2 sine x right? The derivative of cosine x is negative sine x. And so this is exactly the derivative. And then let me remind you what Newton's method says. It says the next x value is equal to the previous x value minus the fraction of the function evaluated at the previous value divided by the derivative evaluated at the previous value. Right? So this is the formula you have for Newton's method. So let's see if we can get from x0 to x1 and then x1 to x2. So in our case, we have x1 equals, well, x naught is pi over 6. And then we have minus the function evaluated at pi over 6, and then the derivative evaluated at pi over 6. So the function evaluated at pi over 6, cosine of pi over 6 is root 3 over 2. So root 3 over 2 times 2, we get a root 3. Separate that out. And then here, pi over 6 times 3 is pi over 2, so we get a minus pi over 2. Sine pi over 6 is 1/2, so we get negative 2 times 1/2, we get negative 1, and then a negative 3. And if you simplify this, you get that this is approximately 0.564, or around that. Okay? And now from here, you would then, for x2, you're going to take 0.564 minus these things evaluated at 0.564. This ratio f of 0.564 divided by f prime at 0.564. But I'm not going to do that because you should get somewhere around, depending on how many decimal places you kept, you should get something around one of these two values. So you actually get, after x0, by x1 you have something that is at least fixed to the first two decimal places, and then the third decimal place maybe is going to be a 4 or a 3 in the end. But depending on what value we choose here, we might get slightly different values here based on the rounding. So just suffice it to say, I got x1, your x2 should be about the same. It should be one of these two. Okay, so let me just remind you what we were doing here. We were trying to use Newton's method to find a solution to an equation that I had written up here, this 2 cosine x equals 3x. And I pointed out a couple things. I pointed out that finding a solution to this equation is the same as finding a solution to the equation cosine x equals 3/2 x. And so I did that as a graph to sort of see if I could get an initial idea of what kind of solution I was looking for. And then we just started using Newton's method on a particular function. And that function was this side of the equation minus this side. Because if 2 cosine x minus 3x equals 0, then 2 cosine x equals 3x. So we had this function over here, 2 cosine x minus 3x, and I said I was looking for zeros of that function, and that's where Newton's method comes in. So I think that is where I was stopping.
Okay, and that's where I'm going to stop helping you to choose your project problem. Today we learned something called linear approximations, and we also reviewed something about quadratic approximations. The appropriate questions to ask at this point is, where are we going to use them? Where are we going to use linear approximations? Where are we going to use quadratic approximations? Now we've seen some examples of optimizations. I helped you to formulate your whole. Now is the challenge. Maybe you need to do a little bit of the research. What are the typical applications of the concept or the method in linear approximations? This is a very important question. And so when we come back on Friday, I'm going to help you to understand some typical examples of linear approximations. Okay? So that's it for today, and make sure you understand that we have only 3 more classes left. Okay? And after that, you need to submit your project. And after that, you need to come back to write for your final exam. Alright? So make sure you submit your project work, which is due starting from November the 21st. It means this Saturday up to next Saturday. Alright? 1 whole week's time for you to submit. Any problem you choose, which is very much typical to the example problems, it works. Alright? So don't forget to submit your project work.